So first of all, let's talk about what a limit is. And here, there's a bunch of math words right here, but let's actually talk about what a limit is. So a limit is designed to be a way for us to try to evaluate a function in a place where we're not sure that there's something there. If it's a normal situation, a lot of the functions that you've studied between algebra 1 and algebra 2 and pre-calc, 99% of those, you don't have to worry about what the limit is, because it's just the same as the point there. Where it's going to get confusing or more difficult, where something like this is going to be required, is when we have discontinuities like holes and asymptotes and all that stuff. And that's where the limit is going to help us figure stuff out in a new way. So first of all, let's start off. These are really, really softball questions, because the whole point is, so like, let's say we've got, with example 1, a constant function, just the number 5. If there's no x there to plug in, right? So here, do we care about what happens when x is 3? No, it doesn't matter. The answer is just the number 5. And that's what it's talking about here, is that if we're taking the limit of a number and making x go to a different number, we don't care about that x, because there's no x here. Take a look at number 2. Yeah, let's look at number 2, 2, 3, and 4. They're all talking about this sort of stuff. If we're taking the limit of a variable x as x goes to c, as x is approaching c, we're getting closer and closer to c, then we're saying, all right, well, let's just plug in c for x. See, it's just, we take c, put it where x goes, everything's fine. Hey, hooray. So like number 2, the limit as x goes to 2, we're just saying, all right, well, let's check to see if it works at 2. Does it work at 2? Let's plug in 2 and see what happens. Well, I can do that, right? That's okay. I'm allowed to plug in 2 in this function. 2 squared is 4 times 4 is 16 plus 3 is 19, right? So in a lot of the cases where we're working with limits, especially in the beginning, it's going to be, hey, here's a fancy way to say, plug in this number. Like here, where we're dealing with this, we're saying, all right, well, there could be a problem if the denominator equals 0. Let's be careful. Let's step back a little bit and make sure that we can actually do this. So we plug in 1, and look what we get. And I can do that, right? Like, this isn't going to come out to be 0 on the bottom, so we know we're okay. 1 squared is 1. 1 and 4 is 6. So we got 6 over 2, and that simplifies to 3, right? Well, so the answer here is 3. And then same thing here. We go over here, and okay, can I plug in pi over 2 for sine? And by the way, this is in radians. So I plug it in, and what do I get? I get sine of pi over 2. And I think for a second, and I go, okay, where's pi over 2 on the unit circle? Pi over 2 is right here. 0.0, 1. So sine, which is the y value, is 1. So the answer here is just 1. So notice, for these limits that we have here, these algebra problems, these algebraic expressions, and we're trying to take the limit as x goes to a number, as x approaches this number, there's nothing different happening than what we did way back in the olden days. This is basically just saying, hey, plug the number in for x and see what you get. All right, does this feel okay so far? It's just, again, we're just taking the number as x goes to that number and we're plugging it in and we're seeing what we get. So I wanted to start off with this because I think a lot of times as we get further, you begin to get bogged down in a lot of the details. And just remember, the whole point of a limit, regardless of how complicated or how simple the problem is to figure out where we're going to. What's it going to be? And so in the case of something like this, hey, what it's going to be is just this, the thing that we plug in. So now what I want to show you is more visually, because I think visually it's going to help us understand what's actually happening in a limit problem. So we want to know the two questions that are important here. What is a one-sided limit and what is a two-sided limit? So one-sided limit is we're saying we're going towards a number from one direction versus the other direction. So let's look here at this first example. Can everybody see x goes to 1 and then there's a little negative sign here? And for this one, x goes to 1 and there's a little positive sign here. It's telling us which way are we coming from. Are we coming from the negative side or are we coming from the positive side? So, and I do mean this honestly, for problems like this, you could just take your finger, put it up on the screen, and then just drag your finger to the right location, like this. So let's look at example 1. For part A, we want to go to 1 from the left. We're coming from the left. We're going towards 1. And we want to know, what are we getting to? Where are we going? What's our end point? It's this one, right? Right here? This thing? That's where it's going. That's where it's approaching. So if you look here, as the limit goes towards, as the function goes towards x equals 1, what's the y value in that spot where we're dragging our finger? And we look, and the y value here is 1, right? Let's go from the other direction. X goes to 1 from the positive side. Well, where's this one going? Well, we're approaching 1. We're approaching, and here's the spot, right? So here it's approaching the x value of 1. So what's the y value at our target up here? What's our y value from here? Isn't that just 2? So we're going to skip C and D for a minute, and we'll talk about the rest of these right now. Take a look here. Left-handed limit. Where am I going? Well, I'm going to 1. What is my value in this spot? Well, it looks like -1, right? Let's do the same thing with the right-handed limit. We're just following along, coming up to the top here. Hey, this is the spot. That's where I'm going towards. What's my y value? 1. Let's do this one now. Take a look. We're going towards 1 again. Limit as x goes to 1 from the left. Limit as x goes to 1 from the right. Y'all see what's going on here? So Here, both sides happen to be approaching the same spot. So what's great is that for both of them, the answer is 1. And same thing here, both of them, the answer is 1. Again, the left-handed limit and the right-handed limit. The limit from the negative side, the limit from the positive side. That's the one-sided limit. We're following along, we're going up, and where does it lead? It may not lead to a point. It may lead to a hole, like it did in all of these examples, right? So, that's sort of the thing. We're just following the trail until we get to where we're supposed to get. A two-sided limit, in order for there to be a two-sided limit, the two one-sided limits have to agree. So look at example number 1. The left-hand limit and the right-hand limit, this one comes to 1, this one comes to 2. They don't match. Since the left-handed limit and the right-handed limit don't match, we know that the limit, the two-sided limit, does not exist. So I just put DNE. And if you want to look impressive, you can say it like this. I'm just writing it out in math speak. It's saying the limit from the left as x approaches 1 of f of x does not equal the limit from the right as x approaches 1 of f of x. So example number 2, take a look. It says the left-handed limit as x approaches 1 goes to -1. The right-handed limit as x goes to 1 approaches 1. Are these the same? No, they're not. So we know, since they're not the same, does not exist. Now, if we look at number 3, you see how they both go to the same place? Both trails converge at this spot. The limit from the left is 1. The limit from the right is 1. So the limit from both sides is 1. And so the limit here is 1. Now, 3 and 4 look very, very similar to each other. The only difference here is this spot down here. This spot has nothing to do with our limit. We go through and we do our limit and we find that, hey, they both come to here. This point down here, garbage, we don't care. It has nothing to do with the limit. The left-handed limit goes to 1. The right-handed limit goes to 1. The two-handed limit is 1. This last thing is saying, what's f of 1? Well, it's saying at 1, what is the value of the function? Where is the actual point at? So if we look here, at 1, I'm going to erase this and try and draw me a line. Let's see, at 1, right? Where's the actual point? It's not here. That's an open circle. We care about where it is up here, right? Care about where it is up here. We want the actual, on the wrong dang one. There we go. We want the actual point. So if we look, the actual value here is this guy right here. It's 2. Let's do the same thing for number 4. And I'm skipping 2 and 3 because they're weird, and we're gonna come back and talk to them in a second. We want to know what f of 1 is, and we look up here, there's no point. That's an open circle, right? So it's not there. Where is it? Oh, it's down here. So what's f of 1 right here? It's where the dot is, at -2. Let's look at this one. Let me erase all that just so it looks clear. There's no dot. There's no dot at 1. If we look at all the spots where x equals 1, this whole vertical little strip, ain't no 1. It's not there. There's no y value when x equals 1. So in that case, hey, it does not exist. Likewise, here, there's 2 points. We can't have 2 points in a row. That violates the vertical line test in Algebra 1, right? You can't have 2 points that are vertically above each other. You cannot have an x value that is given to 2 y values. So as a result, likewise here, does not exist. Okay, so we're talking about why limits don't exist, and we're gonna bust through this real quick because, like with this one, look, it's coming from the left. Where's it going? Ooh, it's going down, 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 down. It keeps on going. This vertical dashed line is an asymptote. That means that this is going to -infinity. Likewise, this one, positive infinity. Does everybody see what's going on here? It doesn't just stop at that point. It keeps on going down, down, down forever, forever, forever. Likewise, this one keeps on going up, 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 up forever, forever, forever. At 2, there's an asymptote. This does not exist. But what about the limit? Well, the thing of it is, the limit's the same as what we were just doing before. Hey, they didn't meet. Like for 1 and 2, they don't meet. So the limit doesn't exist. Here, they don't meet. This one goes to -infinity. This one goes to positive infinity. And I'm sure I could have a really nice long talk with a friend of mine who's really big about infinity, and he could tell you that, well, technically maybe they meet at that infinity coming from both directions, but we're not going to talk about that. That's complicated. But if they go off towards infinity, they're not going off towards a number. So the limit does not exist here either. Here's a couple other examples of the limit not existing. Here you're being asked to find a place where the limit does not exist. And if we look, well, okay, it's all working here. Every spot that I look at, there's, from both directions, they come to be the same, except for here, right? Except for here. Here, there's a ton of them. Look, there's one right here. The limit doesn't exist at this spot at 8. The limit doesn't exist at this spot at 6. It doesn't exist at -2. Doesn't exist at -4 or -6. So these are called jump discontinuities. Because there's a jump. Like you try and get from one spot to the other, and you have to jump to get there, right? Imagine a little dude sledding down the hill, and he comes to the bottom, and is like, oh, I have to jump up here to get to the next spot, and then keeps on going. Same thing here. There's a jump. 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 Anywhere you see a jump, The limit does not exist because it can't. The two directions don't match. Okay. Here is this is a question taken from the 2014 calculus exam. This is taken from the BC exam. The BC does have some AB stuff in it. So, and this is multiple choice question number 5. Now, I will be very honest with you. This structure of question where you've got the 3 things and then the multiple choice, which of those 3 things, is designed to be a time waster. And we'll talk a little bit more about this later, but you know, when you're trying to take a multiple choice test, you always try and split your problems into 3 parts. Part number 1 is, oh, I can get this right now and just answer it. Part number 2 is, I think I know how to do this, but it's going to take a while, so I'm going to set it to the side. And then part number 3 is, oh God, these are all written in Greek. I have no idea what I'm doing. So the way that you go through a multiple choice exam, especially when hopefully by the time we meet back up, it'll be paper pencil. You'll go through, you'll do the ones that you know, you'll come back and do the ones that take a while. And then you've used all of the time that you have to earn the points that you know how to get already. And then the rest of those problems, you can try them. And that's just, you know, extra icing on the cake for you. So, but here, these are designed to be time wasters because you have to go through and figure out basically 3 problems and then figure out which of those 3 problems is good. So we're going to go through this here, and we're going to do it, but a problem like this is definitely a part 2 problem where you go through and you come back for it in a little bit. So we want to know which of these are true. The limit as x goes to -2 equals f of x goes to 2 from the, I'm sorry, the limit as x goes to 2 from the right of f of x equals f at 2. So let's look at 2 from the minus from the left. So coming down here, the limit here, we get -1. What is f at 2? Well, it's also -1, the solid circles right here. Hey, this one is true. So automatically that means, hey, anyone that doesn't contain 1 as an answer, we can get rid of. Let's look at number 2 now. The limit as x approaches 6 from the left is equal to the limit as x approaches 6 from the right. And hopefully by now you're seeing, well, look, coming this way, coming this way. Yeah, they're going to be the same, right? These are both the same. They both go to -1. So 2 is correct. That means anyone that doesn't have 2, we can kick out as well. So we're stuck with, is 3 right, or is it just 1 and 2? So let's look at this one now. Is the limit equal to the actual value? And hopefully you can see, hey, the limit, they're going to -1. The value is actually down here at -3. And that's not true. This is not true. This is bad. So anyone that contains 3, we can get rid of. So the correct answer has to be C. I'm going to pull up problem number 1 just to see. Yeah, so look, true or false. This is true or false. The limit of f of x as x goes to -3 is 9. Well, let's look. I'm going to zoom in so I can see better. As it goes from the right, what do I get at -3? Let's follow -3 all the way up. Hey, That's 9. That's true. True or false? So these are super duper easy, and it will take you all of 3 seconds to do, honestly. Like here, the limit as x goes to 0 is 1. No, it's not. The limit as x goes to 0 is just 0. So it can't be that. True or false? The left-hand limit and the right-hand limit as x goes to 0 are the same. Well, that one goes to 0. And that one goes to 0. So yeah, sure does. True or false? The limit exists. Well, here's the thing. This right here, this third one, that's the test to see whether a limit exists. If the left hand and the right hand match, then the limit exists. That's how it works. True or false? The limit as f of x as x goes to 0 is 0. Well, isn't that what we just said? It goes to 0, right? They both go to 0, so we know that that's true. And now we're going to say true or false. The limit as x goes to 3 is 9. Now, here's the thing with this one. Notice that there's no other side. So I think this should be false. Because it's not a, you can't have a two-sided limit here. Hey, I was right. Good. And the limit as x goes to 6 from the left is 6. And let's look. So this part doesn't enter into it. We're approaching 6. So we're starting in this spot. And so we're like, okay, well, where's it going? Oh, what's the y value here? It's 0. That's not 6. That's false. All right, so each of these is super easy. Each of these little parts are easy, and you're going to be able to just ram through these in a second. And like they give you this here, but they're also going to give you a picture for this one. So don't be afraid to use the picture here for working this out. The picture is what you want to use, okay? So I'm going to really quick look through here and make sure that it's all, yeah, this is fine. Ooh, this one. Okay, let's talk about this one real quick because this one is important. The picture here so this picture is what's called the topologist's curve. And that was sort of a, let me get it so I can see it better. And then let me do this. I have to do it like this. Let me show you what I'm talking about here. Okay, so I'm going to stop sharing this one real quick. And I'm going to start sharing this one real quick. And if you want to work on your own stuff while I'm doing this, like if you're Mr. Webster, I don't need your help on these. That's fine. I wanted to show you this right here. So the way that this curve works is it actually, I want to get this thing. As it goes to, as it approaches this here, this is kind of like an asymptote, but not really. Because what happens is the because you all know what like a sine and a cosine looks like. It sort of wibble wobbles, right? Well, this one, what happens is the curve basically just goes faster and faster and faster. It's tighter and tighter and tighter and tighter and tighter and tighter and tighter until it stops moving and it just sort of stands there scribbling forever. And so this right here, this scribble, right here at -2, is actually all of these numbers at the same time, because it's going so fast, it's actually hitting all those numbers simultaneously. And so is it approaching one number? No, it's not approaching one number. So it does not exist there. I'm looking in. Just be careful with number 2. The way that they've presented it is super dumb. So let me show you what I'm talking about, because they showed it in a they showed what to how to enter your answer in a really stupid way. So just sort of be careful here. Let me show you what I'm talking about. I want to do that one. Share. Okay. So take a look here. With this one, you know, it's obvious that the limit does not exist, and they throw that as one of the 2 answers in there. But look what it says. It's asking for you to find the left and the right-handed limit. So this part B is there to throw you. Ignore that one, because you're going to tell me that the left-handed limit is it's going to 2. The right-handed limit, what's that going to? That's going to, looks like 4, but it looks off. Not quite 4. It's, what does that look like? Maybe 3 1/4 or 4 1/4. I mean, we can plug it in. You see how they give you it right here? It's 9/4 plus 2, so 2 1/4 plus 2, 4 1/4. Tell me how I put them backwards. Let's try that again. Sorry, I put them backwards because I can't read. Okay, that's why I teach math, right? Okay, let's try this again. Hey, okay, good. But just be careful with it. And then it's going to open up this next part. Does the limit exist? Now you're actually going to answer, hey, does it exist or not? No. And the reason is because the left and the right hand limit don't match. So now it's going to go through and it's going to ask you about at 5. So the same thing at 5. Well, what's happening here? Here they're the same, right? That looks like 5.75. Oh, you're supposed to be able to tab through to the other box. 5.75. And again, they give you this other option, but they're not asking about whether or not the limit exists. They're asking about what the left and the right hand do here. And again, now they're asking, hey, does the limit exist? Well, the left and the right are the same, and they make 5.75. So yes, because they're the same, and it's 5.75. Ta-da. So just be careful. And again, same thing here. here it's asking you to find a specific thing. This is an answer that is a non sequitur. Ignore it, because it's not asking does it or doesn't it. It does. The right hand and the left hand limits are always going to exist, right? Unless you're coming like on the side where there is nothing. But the left and the right hand should always exist if you're going towards a point like on a picture like this. So here we're looking to figure it out at 4. The right hand limit, that's approaching 1, right? Now it's asking about the left hand limit. Well, what's the left hand limit? It's approaching 1. The y value is approaching 1. So same thing here. And since the x, the y value is the same for both of them, we know that the limit's going to end up existing. Now let's answer this question. It says find f of 4. Find the value of the function at 4. And that's not where the limit is, right? That's up here at 2. So does the limit exist? Well, yeah, because the left and the right hands match. That's all we care about. We don't care about what the value is. The left and the right hands do match, and that's what matters. And so what we found before, that the limits both converge to 1. So the two-handed limit is 1. And now we can look at this one. They're asking about a different one. They're asking about as we go to 1 from the right. And that gives us 4. As you can see here, there's not a lot of work to be done. We're looking at a graph and we're putting our finger where it goes, and that's all we have to do. What about the other way? Still 4, right? And the limit does exist because the left and the right hand match. We end up with 4, just like we've been doing.